Hello guys, hope you all are doing well. So in the continuation of the previous GATE series, we have completed the question paper 1994, section A and section B, first part. Now we will complete 1994 today. So without wasting time, we'll look into the question. The transfer function of a process, a measuring element and a control wall is given by. We have a transfer function of a process, measuring element and control wall. That is the final control element, control wall. A proportional controller with gain Kc is used. Okay, write a closed loop transfer function related to output to set point. What is the steady state error in the output for a unit step change in the input? So steady state error means it is asking for offset. Okay, so we'll calculate offset. Okay, so very first we will see the diagram. So this will be plus, this will be plus, this, oh sorry, this will not be plus, this will be minus, this will be plus, this will be plus, and this is US, that is load 0, and that is set point of XS, and this is YS. When it is written in the question, servo problem, that means set point, servo problem, set point change, set point will change. Regulatory problem, load will change. Okay, so very first the question is asking for closed loop transfer function. Okay, so closed loop transfer function YS upon XS will be GC, transfer function of controller, GP 1 plus GC GV GP GM. Okay, so putting all the values we will get Kc is 1, GV is 1.5 upon 3S plus 1 into 2 upon 2S plus 1 divided by 1 plus 1.5. This whole term will come. So 1.5 into 2, I will write 3 upon 3S plus 1, 2S plus 1 into GM will come. So 5S plus 1. If you solve this, we will get ultimately 3 up. So this is the final transfer function. Okay, now second part is asking for steady state error. So steady state error means offset, and offset is equal to R infinite minus C infinite, where R is in set point, C is the output. In this case, X infinite minus Y infinite. Okay, so very first we will calculate X infinite, and that means X tend to infinite is equal to limit S tend to 0 S into Fs. Fs for X, that is XS. So X is unit step. So XS will be 1 upon S. So here 1 upon S. So X infinity will be 1. Y infinity, Y tend to infinite. That means limit S tend to 0 S into YS. So S into YS. YS is, so we have YS upon XS is equal to 3 upon 5S plus 1, 3S plus 1, 2S plus 1, 5S plus 1 plus 3. This is ys upon xs, but we need ys only. So excess will come here. What is excess? 1 upon s. Okay, so we will put this whole value here. So 1 upon s we will write in front. Now 3 5s plus 1 upon 3s plus 1 2s plus 1 5s plus 1 plus 3. So s tend to 0, put 0 in place of all s, so 3 will come up, 1 plus 3, so that is 3 by 4. So this is 3 by 4. Now, so put here values. X infinity is 1 minus y infinity is 3 by 4. So offset is 1 by 4, 0.25. Okay, excess is 0.5. So this is a straightforward question. Okay, switching over to the next question. The characteristic equation of a closed loop system is given by. So characteristic equation is this. This is the characteristic equation, and we have to apply. Check whether the system is stable or not. So apply Raoult-Harris. Apply Raoult-Harris. I think this is very easy question, but still I'll solve. S to the power 4, s to the power 3, s to the square, s1, s0, 1, 4, 6, 2, 3. Okay, if you will calculate, here it will come 22 by 4, it will come 0, 0 here, then it will come minus 4 by 22. So the system is not stable, because the condition for stable system is all the elements in the first column of Raoult-Harris array will be non-zero and non-negative, right? So the system is not stable. Okay, switching over to the next question. So cost of a blower in 1980 is rupees 2000. What is the cost of blower in 1988? Okay, so very first, in 1980, cost of a blower is 2000. In 1998 we have to calculate, 1998 we have to calculate, the capacity is same, x letter. Cost index in 1980 is 1988. Sorry, either this will be 1988 or this will be 1999. So I will take this as 1988. So this is 1988. Okay. So x capacity and the cost index at in 1980 is 250, and cost index in 1988 is 300. Actually, what I can recall, this is 1988. Yeah. So we have to find out the cost. Okay, so we'll apply 610 factor rule along with the cost index method. So cost in 1988 will be, very first the cost will come, because we have to calculate the cost, x upon x into 0.6. Okay, 610 factor rule divided by the cost index is 300 divided by 250. So it will come rupees 2400. But what is the cost of blower in 1980 with the double the capacity? So cost in 1980 will be, in which year we are calculating, the cost index of the same year will be in the numerator. So 2400, double the capacity, 2x upon x will be 2.6, 250 divided by 300. So it will give rupees 3031.4. Okay, and this b part is Lang factor. Don't do this. Okay. In a gas mixture of hydrogen and oxygen, so hydrogen and oxygen, H2O2, okay, equimolar counter diffusion is taking place at a total pressure of 100 kilopascal and temperature 20 degrees Celsius. So 273, 283, 293, 293 Kelvin is the temperature. If the partial pressure of oxygen at two planes, 0.01 meter, perpendicular to the direction of the diffusion, 15 kilopascal, 5 kilopascal, okay, respectively. In the mass transfer flux of oxygen, Na, we have calculate the molecular diffusivity. Straightforward formula for equimolar counter diffusion. Na is equal to DAV RTZ PA1 minus PA2. Okay, straightforward. So Na is 1.6 into 10 की power minus 5. We will see the unit in this particular question. Kilomole per meter square second is equal to DAB. We have to calculate. Okay, R 8.314 kilo Pascal meter cube kilomole Kelvin, temperature 293 Kelvin, Z 0.01 meter, PA1 15 minus 5 kilopascal. Okay, now kilopascal and kilopascal will cancel out, kilomole and kilomole will cancel out, meter square there should meter only. So meter square per meter square and per second. That is the unit of diffusivity. So we will get diffusivity DAV (3.8976 into 10 की power minus 5 meter square per second. Okay, straightforward. Okay. A stream of air at 100 kilopascal pressure and 300 Kelvin flowing on the tops. This is top surface. Okay. Top surface of a thin flat sheet of solution of naphthalene of length point. Okay. So this is the sheet, okay, of naphthalene, above which air is, okay, C infinity CAI, interface concentration. Okay, so pressure is 100 and temperature 300 Kelvin. This length is 0.2 meter. Velocity at which the air is going 20 meter per second. Mass diffusivity of naphthalene, kinematic viscosity of air, concentration of naphthalene and air, CAI दिया है interface पे. This is calculate average mass transfer coefficient of over a flat plate, rate of loss of naphthalene per unit width. You may use analogy between mass transfer and heat transfer. Okay, so we have Nusselt number is equal to 0.664, Reynolds number 1 by 2, Prandtl 1 by 3. This formula will give the average heat transfer coefficient. Okay, but we have to find out the average mass transfer coefficient. So we will use the analogy. Nusselt number is analogous to Sherwood number in mass transfer, else remains same, 664. Reynolds number is same, and Prandtl number in heat transfer is analogous to Schmidt number in mass transfer, 1 by 2. Okay, so this is analogy. This will give the average mass transfer coefficient. For local, this term will replace, for local 0.664 replaced by half, 0.332. Okay, so you will learn this when you will go through the book. Okay, so Sherwood number Kc, that is average, L in case of flat plate it is L, and in case of pipe or sphere it is D. KCl DAB. D means diameter, 0.664. This is diffusivity, and here when pipe and sphere will come, then it become diameter. Okay, Reynolds number rho VD upon mu, but we have kinematic viscosity, and we know that Mu by rho is nu. So we will write Vd by nu. Velocity, this is velocity, this is kinematic viscosity. 1 by 2. Smith number, Samoma. Samoma, momentum to mass. Okay, 1 by 3. This is 1 by 3. By 3. Okay, now putting all the values, we will get Kc is equal to, after putting all the values, we will get Kc 0.013989 meter per second, right? Now the flux will be Na is equal to Kc average into Cai minus Ca infinite. Ca infinite is 0. Okay, so well 0.013989 into 10 to the power minus 5 kilomole per meter square second. Okay, straightforward question, just a trick here, and it is given in the question that you can use the analogy. So this is analogy. Okay, so carbon disulfide is to be absorbed from a dilute mixture of gas mixture of CS2 and N2. Okay, so very first we'll draw the diagram. If this is our tower, okay, this is Y1, this is CS2 N2 mixture, okay, and solvent will come here. The solvent is pure, I think, into a pure non-volatile solvent. That means X2 is equal to 0. Solvent, pure solvent, X2 equal to 0. This is, but X1 will not be 0 because the solvent will absorb the CS2. In a counter current absorber, the mole fraction of CS2 in the inlet gas stream, this is mole fraction, this is mole fraction, small y1, 0.005. So capital Y1 will be 0.051 minus 0.05, that is 0.0526. If you have problem in this, then I'll make it clear to you that it is saying that the mole fraction, okay, see, mole fraction means small y1, that is notation. This means 0.05 kilomole of CS2 in the kilomole of mixture, right? Because mole fraction is total given moles of a component to the total moles, so mixture will come. But when I say mole ratio, and so I will write capital Y1, so 0.05, and here is 1. So 0.05 kilomole of CS2 in 1 kilomole of mixture. So I will minus 0.05, then it will become kilomole CS2. Now from 1 kilomole of mixture I have minus 0.05, then it will remain only kilomole of N2. This is the ratio of 2 moles, component A, component B. This is the mole fraction, right? So this is the thing. Okay, now, okay, so, and we will see what we will take into the question. Okay, now, so the flow rate of gas stream is 15 gas stream flow rate. G is 1500. So we have G, and G is the 1500 kilomole mixture, okay, per hour, and GS is the pure component flow rate, that will, like kilomole of mixture. If I want to calculate the flow rate of CS2 only, then what I should do, I will multiply 0.05, then kilomole of mixture and kilomole of mixture will cancel out, then it will give the C like this. So I want to calculate GS, that is the GS pure component mixture of CS2. So 0.05 kilomole CS2 divided by kilomole mixture into 1500 kilomole of mixture divided by hour. So this will cancel out and it will give whatever the value, then kilomole CS2 divided per hour. Okay, then suppose this value is x. 15 5 ja 15 into 5. 75, I think 75 or 5 5 or 25, 5 5 6 7 75, I think, whatever the value. Suppose x. Now 1500 minus x will give the value of the solute free solute free on the basis of the solute free, the flow rate of the gas stream on solute free basis. Okay, this will be the flow rate of gas stream on solute free basis. That means you can see only N2 is there. Okay, so these are the things. Okay, but we will just look into the question now. So the equilibrium relationship is given by this. Okay, x is the mole fraction, x is in liquid and y is in gas phase, that is for sure. Okay, calculate the minimum value L by G when L is liquid flow rate in kilomole per hour. Okay, okay, so we will apply energy balance, we will apply mass balance. G y1 minus y2 is equal to L x1 minus x2. Okay, so G is we have to calculate the minimum liquid to gas ratio. So y1 minus y2, we will not put the value of L and G. L by G x1 by x2 is 0. y1 is 0.05 minus 0.005, we have to reduce it, that is this value. Okay, equal to L by G. Now x1, when for minimum liquid to gas ratio, x1 always come from the equilibrium relation. Write it down. For minimum liquid to gas ratio, x1 always comes from the equilibrium relation. Okay, so when I write here y1 by x1, y1 by 0.5, because it is x1, so y1 by 0.5. If it is x2, then y2 by 0.5, then it become L minimum here. So L by G minimum is equal to 0.05 minus 0.005 divided by, so y1 is 0.05 divided by 0.5. Okay, y1 is 0.05. Okay, this is the value of minimum liquid to gas ratio. So 0.05 divided by 0.5 into 0.05 minus 0.005, 0.45. This is the value 0.45. Now derive an equation for operating line if L by G is equal to the 1.5 times the minimum. So actual L by G actual given in the question in which the tower is operating is equal to 1.5 times the L by G minimum. Okay, so it will into 1.5, 0.675, 0.675. Okay, now we have to so again apply this equation. Okay, we have to derive an equation of operating line. So this equation we have, and G for y1 put y minus y2 is equal to L x1 x minus x2 is 0. So G L by G एक नट L by G y minus y2. Okay, so y is equal to, and this is x, so y is equal to L by G x plus y2 is 0.005. So y is equal to L by G will be 0.675 x plus 0.005. So this is the final equation. Okay, so the equation of final operating line will be y is equal to 0.675 x plus 0.005. Okay, so this is the equation of operating line. Okay. Question. A binary distillation column is operating under the condition specified below. Feed flow rate, overhead product, mole fraction of more volatile component, bottom product rate, reflux ratio. In the stripping section, it was found that the mole fraction of more volatile component is leaving the plate, that is Y, is 0.33, while mole fraction in the liquid, that is X, of the same plate. So at constant molar counter flow determines whether feed is vapor of liquid partially vaporized. Okay, so we have to find Q, value of Q, whether it is superheated, saturated, partially liquid, liquid plus vapor, what is the value. Okay, so for finding Q we have two equations. L dash is equal to L plus QF. V is equal to V dash 1 minus QF. Either of these two equations. Okay. Since we have given the stripping line, since we have given the composition in the stripping section, so we will apply the stripping line equation. Apply stripping line equation. Stripping line equation. Okay. Yn plus 1 is equal to L dash upon L dash minus W xn minus W xw upon L dash minus W. Okay. Now put the values. Yn plus 1 is 0.33. How? I have explained in the previous lectures. So we will find L dash from here minus W. W is bottom product rate, that is 200. Xn is 0.25 minus W 200 into 0.02 bottom product composition 0.02. Okay, minus L dash minus 200. Okay, so here from here we will get L dash is equal to 775. Okay, 775. Now L dash is equal to L plus QF. We have L dash 775. We will need to find L. So R is equal to L by D. Reflux ratio is 3.5. So L is equal to 3.5 into D. D is overhead product rate 150. That will give 525. So 525 plus Q into F is 350. So the value will Q is 0.7143. So it is in 0 and 1. So liquid plus vapor. Okay. Partially vaporized. Okay. So this is the final. So if you have any kind of confusion, anything, just comment it below. I will reply as soon as possible. Okay. So bye guys, take care. So we have completed 1994 and we will start 1995 very soon. Okay, bye.